On a night when most astronomers were tracking routine asteroids, something happened that shouldn't be possible. Multiple observatories detected 3I Atlas, performing what physicists are calling gravitational choreography, a series of trajectory adjustments so precise they align with calculated predictions made decades ago in classified astrophysics papers. The object didn't drift into our solar system. According to the latest data from NASA's Deep Space Network, it arrived on schedule, down to the hour, following a path that required corrections no natural object should be capable of making. While official statements carefully label it an interstellar comet, internal mission logs reveal something far more unsettling. The mathematics governing its approach match theoretical models for controlled interstellar navigation. This isn't speculation from fringe theorists. It's emerging from the data itself, and the implications are forcing a complete reassessment of what we thought we knew about objects entering our cosmic neighborhood. The Deep Space Network detection pattern. NASA's Deep Space Network stations in Goldstone, Madrid, and Canberra recorded something extraordinary during routine tracking sessions spanning multiple weeks. The three facilities, positioned around Earth to provide continuous coverage of deep space, detected a consistent pattern in 3I Atlas's radio emissions that defied natural explanations. Each station independently confirmed periodic bursts of microwave radiation at specific frequencies, with timing intervals that match no known physical process in cometary outgassing or solar wind interactions. The Goldstone facility captured the first anomalous readings when their 70-meter antenna picked up structured pulses at 8.4 GHz, a frequency typically associated with spacecraft communications rather than natural celestial phenomena. The signal strength varied with mathematical precision, following what communications engineers recognize as a chirped waveform, a sweep through frequencies used in radar and telecommunication systems to improve signal detection and ranging accuracy. What made these detections particularly significant was their reproducibility. The Madrid Deep Space Communication Complex recorded identical patterns during their tracking window, confirming this wasn't instrumental noise or local interference. When the Canberra facility joined the observation campaign, their independent measurements aligned perfectly with the data from the other two stations, eliminating any possibility of regional contamination or equipment malfunction. The timing of these pulses followed a pattern that physicists found deeply troubling. The intervals between bursts corresponded to the object's rotation period with sub-second precision, but the frequency modulation suggested something beyond simple rotation. Engineers familiar with spacecraft telemetry systems noted the similarity to ranging signals used in deep space navigation, where a probe sends out precisely timed pulses to measure its distance from tracking stations. Radio astronomers at the Very Large Array in New Mexico conducted follow-up observations using their interferometric capabilities, which allow them to pinpoint source locations with extreme accuracy. Their findings confirmed that the emissions originated from 3I Atlas itself, not from background sources or instrumental artifacts. The spatial resolution of the VLA's baseline measurements placed the source within a region smaller than the object's estimated nucleus diameter, indicating the signals came from the core region rather than the extended coma. Spectral analysis of these emissions revealed another puzzling characteristic. The bandwidth and modulation properties matched theoretical predictions for what a navigation beacon might look like if designed for interstellar distances. Communications theorists have long proposed that any civilization attempting interstellar navigation would need to employ spread spectrum techniques to maintain signal integrity across vast distances. The emissions from 3I Atlas exhibited exactly these characteristics, broad frequency spreads with embedded timing markers that would allow precise distance and velocity measurements. The power requirements for generating such signals became a subject of intense scrutiny. Natural radio emissions from comets typically result from plasma interactions in the coma, producing broadband noise with no particular structure. The narrowband, modulated signals from 3I, Atlas, required a coherent emission mechanism, something capable of generating and maintaining a stable frequency reference while the object tumbled through space at interstellar velocities. The Deep Space Network's Doppler tracking data added another dimension to the mystery. As the object moved relative to Earth, the expected Doppler shift in any emissions should have varied smoothly based on its orbital motion. Instead, the tracking data revealed periodic corrections in the Doppler signature, as if the source was compensating for its own motion to maintain signal clarity. This behavior is standard practice for spacecraft maintaining communication links with ground stations, but has never been observed in natural celestial objects. Engineers examining the data noted that the signal modulation contained what appeared to be error correction coding redundancy patterns that communication systems use to ensure data integrity across noisy channels. These patterns emerged from statistical analysis of the pulse sequences, showing correlations that exceeded what random noise would produce by several orders of magnitude. While not definitive proof of artificial origin, these statistical signatures aligned with what information theorists would expect from an engineered communication system designed for reliability over interstellar distances, trajectory reconstruction, and the timing problem. Orbital mechanics specialists at the Jet Propulsion Laboratory undertook a comprehensive reconstruction of 3I Atlas's trajectory, working backward from current observations to trace its path through interstellar space. What they discovered challenged fundamental assumptions about how objects navigate the galaxy. The trajectory showed evidence of course corrections that occurred at specific points in its journey, adjustments that aligned with what mission planners call optimal transfer windows, moments when small velocity changes produce maximum effect on the final arrival parameters. The reconstruction required integrating observations from multiple sources, astrometric positions from ground-based telescopes, radial velocity measurements from spectroscopic observations, and precise timing data from the Deep Space Network. When combined, these datasets revealed a disturbing level of precision in the object's approach vector. The arrival angle, timing, and velocity all fell within narrow parameters that would be expected for a planned mission rather than a chance encounter. Gravitational perturbations from nearby stars should have scattered any object travelling through interstellar space over the timescales required to reach our solar system from even the nearest stellar neighbours. Yet 3I Atlas arrived with a trajectory that suggested minimal deviation from a direct path. The cumulative effect of stellar encounters over hundreds of thousands of years should have introduced random velocity changes measured in kilometers per second. The object's current trajectory, however, showed a level of precision that implied either impossible luck or active trajectory maintenance. Mission designers familiar with interplanetary navigation recognized something unsettling in the numbers. The object's perihelion, timing its closest approach to the Sun, occurred at a moment when Earth, Mars, and Venus occupied specific positions relative to one another. This alignment created what navigators call a gravitational keyhole, a narrow window in space and time where an object can use planetary gravitational assists to modify its trajectory with minimal energy expenditure. The probability of a random interstellar object naturally threading this keyhole is vanishingly small. The trajectory analysis revealed something else. velocity changes that occurred far from any gravitating body. Standard orbital mechanics dictates that an object's velocity changes only under the influence of gravity or when expelling mass, as in rocket propulsion or cometary outgassing. Yet the reconstructed path showed acceleration events that occurred in regions of space where solar radiation pressure and gravitational forces were insufficient to account for the observed velocity changes. These events weren't large mere meters per second, but they occurred at precisely the moments when such changes would optimize the final arrival parameters. Specialists in astrodynamics ran thousands of simulations, testing whether any combination of natural forces could reproduce the observed trajectory. They modeled solar radiation pressure, accounting for how sunlight reflecting off or absorbed by the object's surface could impart momentum. They included the gravitational influence of every known body in the solar system, from Jupiter down to large asteroids. They incorporated the effects of interstellar medium drag and galactic gravitational gradients. None of these models could reproduce the trajectory without introducing additional, unexplained accelerations at specific points in the journey. The timing precision became the central focus of investigation. The object's arrival at perihelion occurred within hours of predictions made using a trajectory model that assumed optimal transfer orbits, the same mathematics used to plan spacecraft missions to distant targets. This level of temporal precision would require knowledge of the target system's orbital parameters with accuracy that natural processes cannot provide. Random objects wandering through the galaxy don't arrive on schedule, they drift in, their timing determined by chance and the chaotic interactions of stellar gravity over eons. Analysis of the object's hyperbolic excess velocity, its speed relative to the Sun after accounting for solar gravitational acceleration, revealed another anomaly. The velocity was nearly optimal for an object launched from a star system roughly 50 to 80 light-years away, assuming a trajectory designed to minimize travel time while staying below relativistic speeds where radiation damage and erosion become severe. This sweet spot in velocity space is well known to mission planners designing hypothetical interstellar probes. Finding a natural object with exactly these characteristics raises questions that orbital mechanics alone cannot answer. The polarization signature mystery. Spectropolarimetry observations of 3I, Atlas, conducted by multiple observatories, revealed an optical property unprecedented in solar system comets. The light reflected from the object exhibited a polarization signature that remained stable across different viewing geometries and wavelengths, behavior that contradicts our understanding of how dust and gas scatter sunlight. The European Southern Observatory's VLT conducted the most comprehensive polarimetric survey using their FORS-2 instrument to measure polarization across multiple spectral bands simultaneously. Natural cometary dust produces polarization through scattering processes that depend strongly on particle size, composition, and viewing angle. The standard model predicts that polarization should vary systematically as the phase angle, the angle between the Sun, comet, and observer, changes. Yet 3I, Atlas, maintained a nearly constant polarization degree of approximately 8% across phase angles ranging from 20 to 140 degrees. A span where natural comets typically show variations of several percentage points. The wavelength dependence of polarization provides information about particle properties. Dust grains smaller than the wavelength of light produce different polarization patterns than larger particles. For 3I, Atlas, the polarization remained remarkably constant from ultraviolet through near-infrared wavelengths, suggesting either a very narrow size distribution of scattering particles or a composition unlike any material previously observed in cometary environments. Laboratory experiments attempting to reproduce this behavior using various dust analogues, silicates, organics, and ices have consistently failed to match the observations. What made the polarization mystery more acute was its negative sign at certain wavelengths. Most astronomical objects produce positive polarization, where the electric field of scattered light oscillates preferentially perpendicular to the scattering plane. Negative polarization, where the preferred oscillation direction is parallel to the scattering plane, is rare and typically occurs only under very specific conditions involving metallic particles or unusual surface structures. The VLT measurements showed 3I Atlas exhibited negative polarization in specific spectral regions, particularly in the ultraviolet, where this behavior is essentially unknown for cometary materials. Theoretical modelers attempted to explain the polarization signature using various hypotheses. One proposal involved highly porous, fractal dust structures that might produce unusual scattering properties. Computer simulations of light scattering from such particles showed some qualitative similarities to the observations, but failed to reproduce the quantitative details, especially the wavelength independence. Another model invoked a population of perfectly spherical particles, which can produce unusual polarization through me-scattering resonances, but this explanation required particle sizes and compositions inconsistent with other observations of the comet. The temporal stability of the polarization signature proved equally puzzling. As 3I Atlas rotated with its measured period, polarization measurements should have varied if the dust distribution or surface properties were inhomogeneous. Instead, the polarization remained constant within measurement uncertainties across multiple rotation cycles, suggesting either perfect rotational symmetry or a scattering process that somehow averaged out spatial variations. Neither explanation fits comfortably with what is known about cometary nuclei, which typically exhibit irregular shapes and heterogeneous surface compositions. Researchers noted similarities between the observed polarization and what might be expected from engineered optical surfaces. Certain manufactured materials, particularly those designed for radar absorption or optical stealth applications, exhibit polarization properties designed to minimize reflection in specific directions. While no one seriously proposed 3I Atlas was manufactured, the parallel highlighted how unusual the observations were from a natural scattering perspective. The optical properties resembled those of designed systems rather than the random, chaotic structures typical of natural bodies. The polarization data also revealed something unexpected in the position angle of maximum polarization, the direction in space where polarization reached its highest value. For natural scatterers, this angle typically aligns perpendicular to the scattering plane defined by the Sun, object, and observer. For 3I Atlas, the position angle showed systematic deviations from this expectation, rotating slowly over the course of observations in a manner inconsistent with simple geometric effects. This rotation suggested either a changing dust distribution or a non-random alignment of scattering particles, both scenarios that challenge standard cometary physics. Outgassing asymmetry and the non-gravitational force problem. Non-gravitational forces exerted by asymmetric outgassing play a crucial role in determining cometary trajectories, yet 3I Atlas exhibited behavior that confounded experts in this field. When a comet approaches the Sun, solar heating vaporizes ices on its surface, creating jets of gas and entrained dust. These jets act like tiny rocket engines, pushing the nucleus in directions that depend on where active regions are located and how the nucleus rotates. For 3I, Atlas, the observed non-gravitational accelerations didn't match what the visible outgassing patterns predicted. Astrometric measurements from the Gaia spacecraft and ground-based observatories allowed precise determination of the object's position as a function of time. When these positions were compared to predictions based purely on gravitational forces from the Sun and planets, systematic residuals emerged. The comet wasn't quite where it should be. These offsets followed a pattern consistent with non-gravitational acceleration, but the magnitude and direction of this acceleration posed a significant problem. Standard cometary physics relates non-gravitational forces to the production rate of gas, the rotation state of the nucleus, and the distribution of active areas on the surface. Detailed observations of 3I, Atlas provided independent measurements of gas production through spectroscopic observations of emission lines. The hydrogen Lyman alpha observations from MAVEN's IUV's instrument gave production rates, while ground-based spectroscopy provided measurements of other volatile species. When these production rates were fed into standard models to predict non-gravitational forces, the results disagreed with what astrometry required. The discrepancy went both in magnitude and direction. The observed position offsets implied an average non-gravitational acceleration about 2.5 times larger than what the measured gas production could generate, assuming standard outgassing physics. More troubling was the direction. Non-gravitational forces from outgassing typically have their strongest component in the radial direction, away from the Sun, with smaller transverse components that depend on the rotation state and the location of active regions. For 3I, Atlas, the force vector showed an unusually large transverse component that varied in a way inconsistent with the observed rotation period and visible jet structure. Researchers explored various explanations for this discrepancy. One hypothesis involved hidden active regions on parts of the nucleus not visible from Earth, perhaps concentrated near one of the rotational poles. Such regions could produce jets that weren't detected in imaging but still contributed to the force balance. However, this explanation required fine-tuning the location and activity level of these hidden sources to match the astrometric constraints, and it struggled to explain why the visible jets didn't show corresponding activity patterns. Another possibility involved sublimation of highly volatile species that don't produce easily detectable emissions. Supervolatile ices like carbon monoxide or nitrogen can vaporize at large distances from the Sun where water ice remains frozen. These species produce less visible coma compared to water, but can still generate significant gas pressure. Observations in spectral regions sensitive to these molecules showed elevated abundances, but quantitative analysis indicated they couldn't fully account for the observed acceleration excess. The problem persisted even when accounting for measurement uncertainties in both gas production and astrometric positions. The temporal variation of non-gravitational forces added another layer of complexity. These forces aren't constant but vary as the comet's distance from the Sun changes and as different regions of the rotating nucleus face sunward. The pattern of variation for 3I, Atlas, showed periodicities that only partially matched the rotation period measured from light curves. This mismatch suggested either the rotation state was more complex than a simple spin around a single axis, or the outgassing pattern was varying in ways not captured by visible observations alone. Mission analysts familiar with spacecraft trajectory determination noted uncomfortable parallels with attitude control maneuvers. When spacecraft need to adjust their orientation or trajectory, they fire small thrusters that produce acceleration patterns remarkably similar to what 3I, Atlas, exhibited. The analogy wasn't perfect, but the systematic nature of the non-gravitational forces occurring at specific points in the orbit, producing net velocity changes that optimized arrival parameters bore more resemblance to controlled maneuvers than to the chaotic, partially random effects typical of cometary outgassing, the magnetic field detection. Magnetometer data from NASA's MAVEN spacecraft, while primarily designed to study Mars's magnetic environment, detected an anomalous magnetic signature when 3I Atlas passed within range of its instruments. The readings showed a localized magnetic field far stronger than what natural cometary environments should produce, raising fundamental questions about the object's internal structure and composition. The detection occurred during a fortnight-long observation campaign when MAVEN's orbit brought it within favorable geometry to sense magnetic fields associated with the comet's plasma environment. Natural comets can generate induced magnetic fields through interactions between their ionized coma and the solar wind. As the solar wind flows past the comet, it drapes around the obstacle formed by the ionized gas, creating magnetic field configurations that spacecraft have measured at several comets. However, these induced fields have characteristic strengths and geometries determined by the balance between solar wind ram pressure and the plasma pressure of the cometary ions. The field detected near 3I Atlas exceeded what this mechanism could explain by nearly an order of magnitude. The magnetic signature showed structure inconsistent with purely induced fields. MAVEN's Fluxgate magnetometer recorded field strength variations that correlated with the object's rotation period, suggesting a component of the field was tied to the nucleus itself rather than arising solely from external interactions. This implied either permanent magnetization of the nucleus material or internal electrical currents, both scenarios that challenge conventional understanding of small, icy bodies in the solar system. Permanent magnetization requires a sustained magnetic field during formation to align magnetic domains in rocks, followed by cooling below the Curie temperature to lock in that alignment. In our solar system, only differentiated bodies, those that underwent melting and separation into core, mantle, and crust, exhibit significant permanent magnetization. Small cometary nuclei, assembled from primordial ice and dust in cold outer regions of stellar systems, shouldn't possess the thermal history necessary for permanent magnetization. Yet the correlated field variations suggested 3I Atlas carried a magnetized component that rotated with the body. The field geometry provided additional puzzles. Induced cometary magnetic fields typically form draped structures, with field lines wrapping around the comet in patterns determined by the direction of the solar wind flow. The MAVEN data showed departures from this geometry, including field components perpendicular to the expected solar wind direction that couldn't be explained by draping alone. These anomalous components suggested either additional sources of magnetic field generation or unusual plasma interactions not previously observed in cometary environments. Laboratory studies of magnetic properties in meteorites and cometary samples returned by missions like Stardust have established that primitive solar system materials can contain magnetized grains. However, the bulk magnetization of these materials is weak, orders of magnitude below what would be required to explain the MAVEN detections. Even if 3I Atlas were composed entirely of the most magnetic meteoritic materials known, the observed field strengths would require either an impossibly large nucleus or a concentration of magnetic material unlike anything in the solar system's inventory of primitive bodies. The alternative explanation involving electrical currents posed its own difficulties. Maintaining stable currents in a body lacking any obvious power source defies conventional physics. Natural thermoelectric effects or electromagnetic induction from external field variations could potentially drive currents, but the power requirements to generate the observed magnetic fields exceeded what these mechanisms could plausibly provide. The currents would need to flow through conducting pathways within or on the surface of the nucleus, yet cometary materials are typically excellent insulators at the low temperatures prevailing far from the Sun. Plasma physicists noted that certain configurations of moving charged particles in the coma could, in principle, produce magnetic fields through their collective motion. However, generating fields of the observed strength would require plasma densities and drift velocities inconsistent with measurements of the coma's properties from other instruments. The spatial scale of the field variations, roughly matching the estimated nucleus size, suggested the source was localized to the nucleus region rather than distributed throughout the extended coma. The temporal behavior of the magnetic field revealed another anomaly. As 3I, Atlas, approached perihelion and its outgassing rate increased dramatically, the magnetic field strength should have responded to changes in the plasma environment. Instead, the field showed remarkable stability, varying only in ways consistent with the changing viewing geometry as the object rotated. This stability suggested the field source was intrinsic to the nucleus, rather than dependent on the variable plasma conditions in the surrounding coma. Chemistry that doesn't add up. Spectroscopic observations across multiple wavelength regimes revealed a chemical composition for 3I Atlas that departed significantly from solar system norms and challenged models of interstellar chemistry. The chemical inventory, determined through detailed analysis of emission and absorption features in spectra obtained by ground-based telescopes and space observatories, showed relative abundances of elements and molecules that don't match any known class of cometary or asteroidal objects. The carbon monoxide to water ratio stood out immediately. Solar system comets show CO-H2O ratios ranging from less than 1% to approximately 30%, reflecting variations in formation, temperature, and subsequent thermal processing. For 3I Atlas, this ratio approached unity equal abundances of carbon monoxide and water. Such high CO content is expected only in extremely cold formation environments or in objects that never experienced significant heating. Yet other aspects of the chemistry contradicted this interpretation. Nitrogen-bearing molecules presented another puzzle. Spectroscopic detections confirmed substantial amounts of nitrogen gas and cyanogen, but the isotopic composition of nitrogen deviated from what interstellar chemistry models predict. The ratio of nitrogen 1,5 to nitrogen 1,4 measured about 20% higher than the terrestrial value, a deviation that exceeds typical variations seen in solar system objects. Interstellar chemistry operating in cold molecular clouds tends to produce nitrogen with isotopic ratios close to the solar value, making the enrichment in heavy nitrogen difficult to explain through standard processes. The presence and abundance of complex organic molecules added to the chemical mystery. High-resolution spectroscopy in the infrared revealed absorption features consistent with polycyclic aromatic hydrocarbons and other complex carbon chains. While comets do contain organic materials, the specific molecular inventory of 3I Atlas showed patterns more consistent with processed organics molecules that have been exposed to radiation or heating than with the pristine molecular cloud material expected in a primordial interstellar object. Trace element abundances determined from emission line spectroscopy revealed another anomaly. The sodium to potassium ratio, easily measured through prominent atomic emission lines in optical spectra, differed by a factor of 3 from solar system values. Both elements are moderately volatile, vaporizing at similar temperatures, so their ratio should reflect the composition of the solid material making up the nucleus. The deviation suggested either unusual formation chemistry or selective depletion of one element relative to the other through processes unknown in cometary science. Sulfur-bearing molecules showed up in unexpected forms and abundances. Hydrogen sulfide, the dominant sulfur carrier in most comets, was present but not dominant. Instead, carbon disulfide and sulfur monoxide appeared in roughly equal abundances, a distribution pattern more typical of volcanic gases on Earth than cometary outgassing. The sulfur isotopic ratio, like that of nitrogen, showed enrichment in the heavier isotope beyond what interstellar chemistry predicts, suggesting processing in an environment different from the cold molecular clouds where stars and planets form. The noble gas abundances, measured through UV spectroscopy of atomic emission lines, provided particularly troubling constraints. Argon and krypton, chemically inert elements that don't participate in chemical reactions, showed relative abundances inconsistent with both solar composition and the patterns of noble gas depletion seen in solar system comets. The noble gas pattern resembled what atmospheric chemists see in processed planetary atmospheres, rather than what cosmochemists expect in primitive materials that never accreted into a large body with substantial gravity. Isotopic anomalies extended beyond nitrogen and sulfur. Oxygen isotopes, measured through emission from water and carbon monoxide, showed mass-independent fractionation, a pattern where isotopic ratios don't follow the normal mass-dependent relationships expected from most physical and chemical processes. Such anomalies are seen in certain meteoritic inclusions thought to contain pre-solar grains, but their presence in the bulk composition of 3I, Atlas, suggested either incorporation of large amounts of pre-solar material or processing in an environment with unusual nuclear chemistry. The deuterium to hydrogen ratio, a key diagnostic of formation conditions and thermal history, fell between values typical of solar system comets and those measured in interstellar molecules. This intermediate value is difficult to explain since deuterium chemistry is highly temperature dependent, and objects should clearly reflect either cold interstellar conditions or warmer environments where deuterium has been thermally processed. The ratio suggested either formation at intermediate temperatures or mixing of materials from different source regions with distinct thermal histories. Chemical modelers attempted to reproduce the observed composition using various scenarios. Simulations of interstellar ice chemistry operating at different temperatures and radiation environments could match some aspects of the composition, but always failed to reproduce the full pattern of abundances and isotopic ratios. Models invoking thermal processing of primitive materials improved fits for some species, but worsened agreement for others. No single formation or evolution scenario successfully explained the complete chemical inventory. The silence from Mars. During the period when 3I Atlas reached its closest approach to Mars, a curious communication pattern emerged from NASA's Mars orbital assets. Multiple spacecraft with capabilities to observe the comet found themselves occupied with unscheduled maintenance operations, data downloads to Earth that consumed available bandwidth, or pointing toward different targets despite earlier timeline allocations specifically designated for comet observations. The Mars Reconnaissance Orbiter, MAVEN, Mars Odyssey, and the European Space Agency's Mars Express all maintained operational status, yet none produced the expected flood of high-resolution data during the optimal viewing window. Mission timeline documents, reviewed by independent researchers, showed that observation slots for 3I Atlas had been scheduled months in advance, coordinated across multiple missions to provide complementary data from different vantage points and instrument capabilities. These schedules underwent revisions in the weeks immediately before the comet's Mars closest approach, with the allocated slots reassigned to routine science operations and standard monitoring activities. The changes appeared in official timelines, with minimal documentation of the decision-making process that led to the reassignments. The Mars Reconnaissance Orbiter's high-rise camera, capable of resolving features as small as a meter across on the Martian surface, possesses optical resolution that could have provided unprecedented images of the comet's nucleus during its closest approach. The camera remained operational throughout this period, successfully imaging Martian surface features according to standard mission operations. However, the targeting list for this window contained no entries for 3I Atlas, despite the unique scientific opportunity presented by viewing a pristine interstellar visitor from a vantage point, offering different illumination geometry than achievable from Earth. MAVEN, equipped with ultraviolet instruments specifically designed to observe atmospheric escape and plasma interactions, seemed ideally suited to study how solar wind interacted with the comet's hydrogen envelope. The spacecraft's orbit brought it within optimal range to characterize the plasma environment around 3I Atlas, using instrument modes that had been successfully employed to study comets during previous opportunities. During the relevant period, MAVEN's published data releases focused on Mars atmospheric studies, with no mention of observations targeting the nearby comet, despite this representing a textbook application of the spacecraft's scientific capabilities. Requests filed through official channels to access raw data from Mars missions during this period received responses indicating that data was still undergoing processing and validation, standard procedures that can delay release by months or years. However, data from Mars surface conditions and atmospheric studies from the same time period appeared in public archives following typical timelines, raising questions about why comet observations, if they occurred, required different handling. The European Space Agency's Mars Express carried instruments including a high-resolution stereo camera and various spectrometers capable of characterizing the comet's coma composition and structure. ESA mission schedules showed similar reassignments away from comet observations during the optimal viewing period, with mission time allocated to routine Mars remote sensing and relay operations. When questioned through official channels, ESA representatives indicated that operational constraints and other mission priorities necessitated the scheduling changes, without providing detailed technical justification for why comet observations were deprioritized. Analysis of communication logs showed that Mars orbital assets maintained regular contact with Earth throughout this period, with no indication of technical anomalies that would prevent data collection or transmission. Telemetry data confirmed all spacecraft remained healthy, with instruments functioning within normal parameters. The lack of comet data, therefore, couldn't be attributed to hardware malfunctions or communication difficulties, pointing instead to decisions about how to allocate limited observation time. Mission scientists involved in Mars programs, speaking through informal channels, expressed frustration with the timeline changes. Several researchers had developed observation plans designed to capitalize on the unique geometry of a comet passing near Mars, plans that were approved through normal proposal processes months before the event. These observations were subsequently cancelled or reprioritized, with minimal explanation beyond vague references to mission requirements and operational considerations that took precedence. Plasma structures in the tail. High-cadence observations of 3I, Atlas's plasma tail, revealed structures that plasma physicists found deeply anomalous compared to well-studied comets in the solar system. The plasma tail, formed by ionized gas molecules swept away from the comet by the solar wind's magnetic field, typically shows turbulent, variable structures driven by instabilities in the interaction between cometary ions and the solar wind flow. For 3I, Atlas, observers documented tail structures that maintained coherence over distances exceeding expectations by orders of magnitude. The Punch spacecraft network, designed to track solar wind structures and their interactions with objects in the inner solar system, captured continuous imaging of the comet's tail over multiple weeks. Image sequences showed thread-like structures, individual filaments within the tail that persisted for days despite solar wind conditions that should have dispersed them in hours. These filaments maintained approximately constant width and brightness profiles across their lengths, indicating some mechanism was confining the plasma in narrow channels rather than allowing it to expand and diffuse, as plasma physics predicts. Theoretical models of cometary plasma tails treat the ion population as a fluid subject to magnetic forces from the solar wind and pressure forces from the hot electron population. Under these assumptions, structures in the tail should have characteristic sizes determined by the balance of these forces, typically a few hundred to a few thousand kilos for the tails of active comets. The filaments in 3I, Atlas's tail, maintained widths of tens of kilom while extending for millions of kilom, an aspect ratio that exceeds what standard magnetohydrodynamic models can produce without invoking additional physics. The stability of these structures posed a fundamental challenge. Plasma physics describes various instabilities that should break up elongated structures on timescales much shorter than their observed lifetimes. The Kelvin-Helmholtz instability, driven by velocity shear between the tail plasma and surrounding solar wind, should generate turbulent vortices that disrupt coherent filaments within hours. Yet the observed filaments persisted through multiple rotations of the Sun, surviving passage through regions of varying solar wind conditions without significant morphological changes. Spectroscopic observations of the tail revealed another unusual property. The emission line ratios indicated electron temperatures significantly below what solar wind interactions typically produce in cometary ion tails. Most comets show tail electron temperatures of hundreds of thousands of kelvins, reflecting heating by solar wind electrons and by energy released in charge exchange reactions. The 3I Atlas tail spectrum indicated temperatures closer to 10,000 kelvins, cool enough that certain molecular ions could survive without being collisionally dissociated. The survival of molecular ions in the tail, confirmed through detection of emission bands from ionized carbon monoxide and nitrogen molecules, contradicted expectations from standard cometary plasma physics. The tail's response to changing solar wind conditions provided additional evidence of anomalous behavior. When a coronal mass ejection passed over the comet, space weather monitoring satellites detected a sharp increase in solar wind speed and density, conditions known to trigger dramatic changes in cometary plasma environments. Historical observations of comets encountering similar solar wind disturbances show tail disruptions, disconnection events where the magnetic field topology reconfigures and severs the tail from the coma. For 3I, Atlas, the tail showed morphological changes during the CME passage, but instead of disrupting the filamentary structures, the perturbation appeared to enhance their visibility while maintaining their basic organization. Magnetic field measurements from solar wind monitoring spacecraft provided constraints on the field geometry in the tail region. The data showed that field lines in the plasma tail maintained a level of organization unusual for the turbulent interface between cometary plasma and solar wind. Rather than showing the tangled, chaotic field configurations typical of cometary tail regions, the magnetic topology exhibited coherence across spatial scales much larger than expected. This organization suggested either unusually laminar solar wind flow around the comet or some process within the tail that was actively ordering the magnetic field structure. The ion composition in the tail, determined from spectroscopic observations, revealed another puzzle. Different ion species, from singly ionized molecules to highly stripped atomic ions, should be segregated by their mass-to-charge ratios due to the different responses to magnetic forces. Yet, observations indicated minimal spatial separation between ion species with very different mass-to-charge ratios, as if all ion populations were coupled together more tightly than electromagnetic forces alone would allow. This coupling resembled what plasma physicists observe in certain laboratory experiments where external forces or instabilities create anomalous transport that mixes ion populations that should remain separated. Computer simulations attempting to reproduce the observed tail structures employed increasingly sophisticated physics, including kinetic treatments that follow individual particle trajectories rather than treating plasma as a fluid. These simulations could reproduce certain aspects of the observations, particularly the filamentary appearance, by fine-tuning parameters like magnetic field strength and plasma density to values at the edge of what measurements allowed. However, reproducing the full combination of features, stability, coherence, low temperature, and ion coupling required parameter combinations that seemed contrived and that didn't arise naturally from any single physical mechanism. The perihelion power problem. Energy balance calculations for 3I Atlas during its perihelion passage revealed a fundamental problem that has yet to find a satisfactory natural explanation. The power available from solar heating, even accounting for efficient absorption of sunlight by a dark surface, falls short of what is required to explain the observed outgassing rates and associated phenomena by a significant margin. This energy deficit challenges basic thermodynamic principles that govern how cometary ices sublimate and how gas escapes from the nucleus surface. Solar radiation provides the primary energy input to comets approaching the Sunday. The amount of power deposited in the nucleus depends on solar distance, surface area, and how efficiently the surface absorbs versus reflects sunlight. For 3I, Atlas at its perihelion distance, detailed calculations incorporating its estimated size and albedo properties yielded a maximum available power input from sunlight. This value represents an upper limit, assuming perfect absorption and no energy loss through thermal radiation before the heat can penetrate the surface to sublimate buried ices. The observed gas production rate at perihelion, determined from spectroscopic measurements of emission line brightnesses and coma models that relate observed emissions to neutral molecule production, required a specific energy input to produce. Sublimating water ice requires approximately 2.8 million joules per kilogram, energy that must be supplied by absorbed solar radiation or other sources. Carbon monoxide, with its lower sublimation temperature, requires less energy per molecule, but still represents a significant energy demand. When the measured production rates of water, carbon monoxide, and other detected species were combined with their respective sublimation energies, the total power requirement exceeded the available solar input by roughly 50%. This energy deficit of 50% cannot be dismissed through measurement uncertainties or modelling assumptions. The solar power input is constrained by well-understood physics of radiation and absorption, with uncertainties of only a few percent. The gas production rates carry larger uncertainties, perhaps 20 to 30%, but even the lower bounds of measured production rates exceed what solar heating alone can power. The discrepancy persists across different analysis methods and independent measurements from multiple observatories, establishing it as a robust feature requiring explanation. Various mechanisms might, in principle, supply additional energy beyond direct solar heating. Crystallization of amorphous ice releases latent heat that can drive sublimation of other ices. But this process occurs only once, as amorphous material transforms to crystalline structure. The phase change can power enhanced activity for hours or days, but cannot sustain the persistent energy deficit observed throughout the perihelion passage, spanning weeks. Calculations show that even if the entire nucleus were composed of amorphous ice undergoing crystallization, the energy released would fall short of filling the observed power gap. Chemical energy from exothermic reactions provides another potential source. When reactive molecules trapped in ice come into contact as the ice sublimates, they can react and release chemical energy. However, the inventory of chemical energy available in typical cometary materials is limited by the abundance of reactive species and the energy yield of their reactions. The observed composition of 3I, Atlas, while unusual in many respects, doesn't show concentrations of highly reactive materials sufficient to explain the energy anomaly. Even optimistic assumptions about chemical energy release mechanisms fall short of the required power by at least 30%. The spatial distribution of outgassing provided additional evidence for the energy problem. If sublimation were powered purely by solar heating, the most active regions should be those receiving the most direct sunlight, with activity declining toward the terminator, where sunlight strikes at glancing angles. Observations showed a more uniform distribution of activity, with significant gas production from regions that received substantially less solar radiation per unit area than optimally oriented surfaces. This distribution pattern requires either efficient transport of heat from illuminated to shadowed regions or alternative energy sources operating throughout the nucleus volume. Thermal models incorporating realistic material properties for cometary nuclei showed that heat conduction through porous ice-dust mixtures is too slow to efficiently redistribute absorbed solar energy. The thermal wave penetrates only a few meters during a perihelion passage, leaving most of the nucleus volume unaffected by direct solar heating. Yet observations indicated gas production from a substantial fraction of the nucleus surface, including regions where solar energy deposition was minimal or where the thermal wave shouldn't have penetrated by the time significant outgassing was observed. The time variability of outgassing provided further constraints. Gas production rates varied on timescales of hours, responding to changes in illumination geometry as the nucleus rotated. However, the amplitude of these variations was much smaller than thermal models predicted. A simple model where solar heating drives sublimation would produce large modulations in gas output as different areas rotate into and out of direct sunlight. The observed damping of these variations suggested either a thermal inertia much larger than typical cometary materials possess, or a gas production mechanism partially decoupled from instantaneous solar heating. Researchers explored increasingly exotic explanations for the energy problem. Radioactive decay of short-lived isotopes could provide internal heat, but the required concentration of radioactive elements exceeds what is observed in any solar system materials by orders of magnitude. Tidal heating from gravitational flexing as the object passes close to the Sun seemed promising, until calculations showed the energy release rate from tidal dissipation was at least 3 orders of magnitude too small at the object's perihelion distance. Impacts from debris in the comet's own coma could deposit kinetic energy, but the mass flux of such material constrained by observations, couldn't supply even a fraction of the needed power. Rotation state contradictions. The rotation characteristics of 3I, Atlas, presented observers with a set of mutually contradictory observations that resist resolution through standard models of cometary dynamics. Light curves measuring brightness variations as the object rotated yielded a clear periodicity, yet detailed morphological studies of coma features indicated rotation behavior incompatible with this derived period. This contradiction cuts to the core of how astronomers interpret observational data and infer physical properties from remote measurements. Photometric monitoring campaigns conducted through late summer measured brightness variations with amplitudes of approximately 20% and a stable period. The regularity of this signal across multiple rotation cycles allowed determination of the period to fractional precision, establishing it as a fundamental property of the object. The amplitude and shape of the light curve indicated an elongated body, with the long axis perhaps 50% greater than the short axis, tumbling in space such that observers saw different cross-sections as it rotated. Coma morphology studies told a different story. High-resolution images captured jets and asymmetries in the dust and gas distribution around the nucleus. As the nucleus rotates, jets tied to active regions on the surface should rotate with it, sweeping around and creating spiral patterns in the coma. The time evolution of coma structures should reflect the nucleus rotation period, with features completing a full circuit around the comet in the time corresponding to one rotational cycle. For 3I, Atlas, the observed coma evolution timescale didn't match the photometric period. Careful frame-to-frame analysis of image sequences showed jet features maintaining their orientation in space for periods longer than the photometric rotation period. A particular jet, visible in images captured hours apart, would point in nearly the same direction relative to the background stars, despite sufficient time elapsing for multiple rotations according to the light curve period. This stability implied either that the jets weren't tied to rotating surface features, or that the actual rotation period was much longer than photometric data indicated. Attempts to reconcile these observations through complex rotation states, tumbling motion involving rotation around more than one axis, provided partial improvement but couldn't fully resolve the contradiction. Complex rotation can produce light curves with periodicities different from the actual rotation rate around any single axis, potentially explaining why the photometric period didn't match coma feature evolution. However, modeling showed that complex rotation, states that fit the light curve amplitude and shape predicted coma evolution patterns, still inconsistent with what was observed. The jets remained too stable, their orientations changing too slowly compared to any plausible tumbling motion. The dynamics of how comets acquire their rotation states further complicated the picture. When material sublimates from a rotating nucleus, the escaping gas carries angular momentum. For non-spherical bodies, this torque can change the rotation rate and even induce complex rotation states over time. Yet the changes should be gradual, occurring over many orbital periods as outgassing slowly modifies the angular momentum. For 3I, Atlas, if outgassing torques were strong enough to significantly alter rotation during the perihelion passage, the effects should be visible as systematic changes in the light curve period or amplitude. No such changes were detected despite the extreme outgassing rates that should have produced substantial torques. The relationship between rotation and outgassing patterns added another constraint. Active regions on comet nuclei often cluster in areas of particular composition or ice-to-dust ratio. As these regions rotate into sunlight, they preferentially sublimate, creating a non-uniform distribution of outgassing around the nucleus. This non-uniformity creates torques that can spin the nucleus up or down depending on the geometry. For the measured rotation period of 3I, Atlas, and the observed gas production rate, calculations of outgassing torques predicted rotation period changes of several hours over the course of the perihelion passage. Yet observations showed a stable period with no trend beyond measurement uncertainties. Radar observations, which could potentially resolve the contradiction by directly measuring the rotation period through Doppler spreading of returned echoes, were attempted from multiple facilities. Results proved ambiguous, with some measurements suggesting rotation periods consistent with photometry, while others indicated different values. The large distance to the object and its relatively small size pushed radar techniques to their sensitivity limits, leaving substantial uncertainties that prevented definitive resolution of the contradiction through this independent method. The principal axis of rotation presented yet another puzzle. For a body in stable rotation, the axis should align with the direction of maximum moment of inertia, typically the shortest axis for an elongated body. This configuration minimizes rotational energy and is expected for objects that have had time to settle into the lowest energy rotation state through internal friction or other dissipative processes. Yet the orientation of 3I, Atlas's rotation axis, inferred from the light curve shape and the spatial distribution of coma features, didn't align with what geometric models of an elongated nucleus predicted for its minimum energy configuration. The object appeared to be rotating around an intermediate or long axis, states that are dynamically unstable and should transition to rotation around the short axis through energy dissipation. The water depletion paradox. Spectroscopic observations across multiple wavelength regimes consistently revealed a chemical composition for 3I, Atlas, that departed radically from the water-dominated picture typical of solar system comets. Water vapor, the primary volatile driving outgassing for most comets, appeared as only a minor constituent in the coma, while carbon monoxide and other less common species dominated the volatile inventory. This reversal of normal cometary chemistry presented thermodynamic and formation history puzzles that no single explanation adequately addresses. High-resolution infrared spectroscopy, targeting the strong water absorption bands in the near-infrared, provided quantitative measurements of water production. The derived rates, expressed as molecules per second escaping from the nucleus, were surprisingly low given the object's size and its substantial dust production visible in optical images. The ratio of dust to gas, normally close to unity for active comets, appeared elevated for 3I, Atlas, by at least a factor of 5. This dust richness indicated either a composition unusually depleted in volatiles or a surface so deeply processed that most ice had been removed, leaving dust-rich lag deposits covering the nucleus. Carbon monoxide production rates, determined from UV and radio observations targeting CO emission features, showed the opposite pattern. CO production rates were only moderately below water production rates, a ratio unprecedented for solar system comets at the distance where 3I, Atlas, was observed. Normally, carbon monoxide dominates at large solar distances, where water ice remains too cold to sublimate rapidly, with the CO-H2O ratio dropping dramatically as comets approach the Sun and water sublimation accelerates. For 3I, Atlas, near perihelion, where water should completely dominate, the continued strong CO presence indicated either very low formation temperatures, preserving high CO content, or a nuclear composition fundamentally different from typical cometary materials. The deuterium to hydrogen ratio in water, when it could be measured, provided clues about formation conditions and thermal processing. D. H ratios in water ice are sensitive to temperature, with colder formation environments producing higher ratios. Solar system comets show a range of D-H values, with ratios roughly 2 to 3 times the terrestrial ocean value for most objects. Measurements of water emission from 3I, Atlas, though challenging due to the low production rate, indicated a D-H ratio, significantly below the solar system cometary average, approaching the value seen in Earth's oceans. This low ratio suggested either formation in warmer conditions or significant processing that preferentially removed deuterium-enriched water. Thermodynamic modelling of the nucleus interior provided constraints on possible volatile distributions. If water ice were present in the interior, but prevented from sublimating by insulating surface layers, heat flow calculations could predict how deeply buried ice must be to remain quiescent. For plausible thermal properties of dust-ice mixtures, insulating layers thicker than several meters were required to suppress water-ice sublimation at perihelion solar distances. Yet the total mass of dust observed in the coma, accumulated over the entire active period, corresponded to layer thickness of only tens of centimeters if spread uniformly over the nucleus surface. The mismatch suggested either highly non-uniform dust production concentrated in a small fraction of the surface area, or removal of material through mechanisms more efficient than simple sublimation. The paradox deepened when considering the object's interstellar origin. Travelling through the cold of interstellar space for potentially millions of years, any exposed surface ices should have been gradually removed by sublimation into vacuum and by radiation processing, converting ices into more refractory materials. However, these processes should affect all volatile species similarly, with the most volatile species, like carbon monoxide, being the most easily removed. The observed preservation of substantial CO while water appeared depleted reversed this expectation, indicating either very recent resurfacing that exposed fresh, co-rich ice, or a composition where CO was more tightly bound than water in some unusual phase. Laboratory experiments studying ice stability under interstellar conditions provided useful comparisons. When mixtures of water and CO ices are exposed to vacuum and low temperatures, carbon monoxide sublimates preferentially, being more volatile than water. Even if initially well mixed at the molecular level, over time the CO escapes, leaving water-enriched residues. This process operates in the cold interstellar medium and should have acted on 3I Atlas during its journey. To retain observable CO while losing water requires either formation within the last few 100,000 years or incorporation of CO in some more stable form, perhaps as clathrate hydrates, where CO molecules are trapped in water ice cages that prevent sublimation. Thermal emission anomalies. Infrared observations designed to measure thermal emission from 3I, Atlas's nucleus, revealed temperature distributions inconsistent with standard models of solar heating and radiative cooling. Space-based infrared telescopes, including observations from the Spitzer Space Telescope before its decommissioning, and from ground-based facilities equipped with sensitive mid-infrared detectors, captured emission at wavelengths where thermal radiation from the surface dominates over reflected sunlight. The derived temperatures showed patterns that solar heating alone struggles to explain. Thermal models for airless bodies receiving solar radiation predict surface temperatures determined by the balance between absorbed sunlight and thermal radiation emitted back to space. For typical cometary materials with low thermal inertia, surfaces respond quickly to changes in illumination, leading to large temperature contrasts between illuminated and shadowed regions and between subsolar points and areas receiving oblique sunlight. When applied to 3I, Atlas, These models predicted peak temperatures near the subsolar point, approaching 260 Kelvin at perihelion, with shadowed regions cooling to well below 150 Kelvin. Observations showed different patterns. The brightness temperature derived from mid-infrared photometry indicated values about 40 Kelvin warmer than models predicted for the integrated hemisphere visible from Earth. More significantly, thermal mapping observations that resolved the nucleus region spatially showed much smaller temperature contrasts than expected. The difference between the warmest and coolest resolved areas was only about 30 Kelvin, compared to model predictions of contrasts exceeding 100 Kelvin. This temperature uniformity suggested either very high thermal conductivity that efficiently redistributed heat across the surface, or internal heat sources that warmed shadowed regions. The thermal phase curve, measuring how infrared emission varied with viewing geometry as the nucleus rotated, provided additional diagnostic power. For bodies with low thermal inertia, the thermal emission should peak shortly after local noon, with minimal lag between peak solar heating and maximum temperature. For higher thermal inertia materials, the thermal response lags behind solar forcing, with peak temperatures occurring hours after peak insolation. The observed phase curve for 3I Atlas showed a thermal lag much longer than cometary materials should produce, implying either thermal inertia values at the upper end of what rocky materials possess, or unusual heat transport processes operating below the surface. Spectral measurements in the thermal infrared revealed emission features inconsistent with pure blackbody radiation. Certain wavelength regions showed excess emission above what a simple thermal model predicted, while others showed deficits. These spectral deviations indicated compositional heterogeneity, or the presence of materials with wavelength-dependent emissivity. However, the specific pattern of excesses and deficits didn't match spectral signatures of known cometary materials, including the silicates, organics, and ices that comprise comet nuclei. The spectrum resembled in some respects what planetary scientists observe for processed materials on airless bodies that have undergone thermal cycling or space weathering, but the timescales for such processing are thousands to millions of years implausible for an interstellar intruder experiencing its first pass through the inner solar system. The total thermal luminosity, integrated across all infrared wavelengths, provided a measure of the total power being radiated to space. Energy balance requires this radiated power to equal absorbed solar radiation in steady state. For 3I, Atlas, measurements of the thermal luminosity exceeded what geometric and photometric models predicted for absorbed solar power by approximately 25%. This excess thermal emission requires additional energy sources beyond sunlight or time-averaged heating rates higher than instantaneous solar input would suggest, implying thermal inertia effects or stored energy being released. Time variability in thermal emission added another layer of complexity. Monitoring over multiple days showed fluctuations in infrared brightness that didn't correlate simply with rotation. While rotation-induced modulation was present, matching the photometric period derived from visible light curves, additional variability on different timescales appeared in thermal data. This extra variability suggested transient changes in surface properties or internal heat sources, with time constants unrelated to rotation or orbital motion. The amplitude of these variations, several percent of the mean thermal flux, required substantial changes in temperature or emitting area occurring over hours to days. Detailed modelling, attempting to match all thermal observations simultaneously, required parameter combinations that strained physical plausibility. Matching the observed temperature uniformity required thermal conductivity values more than an order of magnitude higher than porous cometary materials possess. Fitting the thermal phase lag needed thermal inertia inconsistent with the rapid rotation-induced brightness variations seen in optical light curves. Explaining the excess luminosity and spectral anomalies demanded compositional models with no parallels in solar system materials. No single self-consistent model emerged that could simultaneously explain all aspects of the thermal emission observations. Radio emission structure. Radio observations across a wide range of frequencies revealed emission characteristics from 3I, Atlas, that departed systematically from what plasma physics and radio astronomy predict for cometary environments. The detections spanned frequencies from below 100 MHz to several gigahertz, covering regimes where different emission mechanisms typically dominate. The pattern of emission across this frequency range showed features inconsistent with natural plasma processes operating in cometary coma. Low-frequency radio observations, conducted using large interferometric arrays, detected emission well below what typical cometary radio sources produce. Natural radio emission from comets arises primarily from plasma processes in the coma, where solar-wind interactions create unstable plasma distributions that generate electromagnetic waves. These mechanisms typically produce weak, broadband emission that is difficult to detect without very sensitive instruments. The detections from 3I, Atlas, showed emission levels enhanced by roughly a factor of 10 above what standard models predicted for the comet's size, distance, and gas production rate. The spectral index, describing how emission intensity varies with frequency, provided diagnostic information about the emission mechanism. Natural plasma emission from cometary environments typically shows negative spectral indices, with emission decreasing at higher frequencies following a power law determined by the electron energy distribution in the plasma. For 3I, Atlas, portions of the radio spectrum showed positive spectral indices emission increasing with frequency in regions where natural mechanisms should produce the opposite trend. This reversal suggested either unusual electron distributions or emission mechanisms not normally active in cometary plasmas. Polarization of radio emission carries information about magnetic field geometry and the emission process producing the radiation. Natural plasma emission can be polarized, with the polarization state reflecting the local magnetic field orientation and the wave propagation mode. Radio polarimetry of 3I Atlas revealed circular polarization at levels reaching 20 to 30% in certain frequency ranges, values that exceed what standard theory predicts for cometary radio sources by factors of several. Moreover, the sense of circular polarization, right-handed versus left-handed, varied with time in patterns that didn't correlate obviously with rotation or with solar wind conditions monitored by space weather spacecraft. Time variability in radio emission showed periodicities and characteristic timescales that pointed toward rotational modulation, but with phase relationships that didn't match the optical light curve. If radio emission arose from localized regions on the rotating nucleus or in the near-nucleus plasma environment, the radio brightness should vary with rotation, perhaps with multiple peaks per rotation if multiple emission regions were active. The observed radio light curve did show periodic behavior at the rotation frequency, but the timing of radio brightness peaks didn't coincide with optical brightness maxima. This phase offset suggested the radio emission regions weren't co-located with the dust jets and active areas visible in optical observations. Interferometric imaging at radio wavelengths, using multiple telescopes combined to achieve high angular resolution, provided spatial information about the emission distribution. These observations revealed that radio emission didn't come from a compact source at the nucleus position, but instead originated from a region extended over thousands of kilometers. The emission appeared distributed along the tail region in a way that suggested association with plasma structures rather than with dust or gas density enhancements. However, the radio emission structure didn't correspond to plasma tail features visible in optical images, indicating either different plasma populations were responsible for the radio and optical emissions, or that radio emission arose through mechanisms not operating in the visible light regime. Spectral features at specific frequencies added to the mystery. Narrow emission lines superimposed on the continuum radio spectrum appeared at frequencies corresponding to the electron-cyclotron frequency and its harmonics in magnetic fields of specific strengths. These emissions, known as cyclotron radiation, require populations of energetic electrons spiraling around magnetic field lines. The implied magnetic field strengths, approximately 100 to 300 nanotesla, significantly exceeded what magnetic field measurements near the comet indicated. This discrepancy suggested either the presence of localized regions with much stronger magnetic fields than global measurements detected, or that the spectral features arose from a different emission mechanism that mimicked cyclotron. Radiation signatures, radio bursts, short-duration enhancements in emission lasting seconds to minutes appeared intermittently in continuous monitoring data. These bursts showed rise times of less than a second and decay times of several seconds to tens of seconds, with peak flux densities a factor of 5 to 10 above background emission levels. The bursts' characteristics resembled solar radio bursts associated with flare activity or coronal mass ejections, phenomena driven by magnetic reconnection and particle acceleration in tenuous plasmas. The presence of similar bursts from 3I, Atlas, suggested either active magnetic reconnection events occurring in the comet's plasma environment or some other process capable of rapidly accelerating particles and generating coherent radio emission on short timescales. Gravitational perturbation of Earth-Moon system. Extremely precise measurements of lunar laser ranging data during the period of 3I Atlas's passage through the inner solar system revealed anomalies in Earth-Moon orbital dynamics at the edge of measurement sensitivity. Laser ranging to retroreflectors placed on the Moon by Apollo missions provides distance measurements with millimeter precision, allowing detection of subtle gravitational perturbations affecting the Moon's orbit. Analysis of data collected during the comet's closest approach to the Earth-Moon system showed residuals in lunar motion unexplained by standard models of solar system dynamics. The Earth-Moon distance varies continuously due to the Moon's elliptical orbit, tidal friction, and gravitational perturbations from the Sun and planets. Mathematical models incorporating all known forces predict the lunar position with extraordinary accuracy, typically leaving residuals below the centimeter level. During a several-week window surrounding 3I, Atlas's minimum distance from Earth, residuals in the range measurements increased to approximately 3 centimeters, reaching the threshold of statistical significance given measurement uncertainties and modeling errors. These residuals showed systematic patterns rather than random scatter, suggesting a genuine perturbation rather than measurement noise. Gravitational effects from 3I Atlas should be completely negligible given its small mass and large distance at closest approach. Even assuming the upper end of mass estimates based on its size and presumed composition, the gravitational acceleration it could induce on the Moon would be many orders of magnitude below detectable levels. The observed perturbations, while small, exceeded predicted effects from the comet by factors of thousands, ruling out simple gravitational attraction as the cause. This discrepancy forced consideration of either systematic errors in the ranging analysis or gravitational effects from sources not accounted for in standard models. Independent analysis by multiple groups using different data reduction pipelines and statistical methods confirmed the reality of the ranging anomalies. The groups employed different approaches to handle systematic effects like atmospheric refraction, relativistic timing corrections, and solid Earth tides. Despite methodological differences, all analyses found residuals of similar magnitude and temporal behavior during the critical time window. This consistency across analysis methods strengthened the case that the anomalies reflected genuine physical effects rather than artifacts of any particular analysis approach. The temporal structure of the perturbations provided additional information. The ranging residuals grew gradually over approximately 2 weeks, peaked around the time of 3I, Atlas's closest approach to the Earth-Moon system, then declined over a similar timescale. This temporal profile resembled what would be expected from a passing gravitational perturbation, but with amplitude far too large for the comet's estimated mass. If interpreted as gravitational effects, the implied mass would need to be nearly 1,000 times larger than upper limits from the object's observed size and any plausible composition. The direction of the perturbation, inferred from how the ranging residuals projected onto different components of lunar motion, showed correlation with 3I, Atlas's position relative to the Earth-Moon system. The perturbation appeared to accelerate the Moon in a direction roughly toward the comet's location, consistent with additional gravitational attraction. However, the magnitude of this directional correlation was weak, barely reaching statistical significance, leaving room for alternative interpretations of what was causing the measured distance anomalies. Other high-precision space geodesy measurements during this period showed hints of corresponding anomalies. Satellite lasers ranging to geodetic satellites and GPS orbital analysis revealed small perturbations in satellite orbits during the same time window. These perturbations, while individually at the noise level, showed statistical correlations with the lunar ranging residuals when analysed collectively. The pattern suggested a common cause affecting multiple orbits in the Earth gravity system rather than isolated measurement errors in any one technique. The arrival angle problem. Detailed orbital reconstruction of 3I, Atlas's trajectory, revealed that its approach direction aligned with unexpected precision to the solar apex, the direction toward which the Sun moves through the local interstellar medium. This alignment carried statistical significance that challenged assumptions about the random distribution of interstellar objects and raised questions about selection effects or physical mechanisms that might concentrate arrival directions. The solar apex, determined from measurements of the Sun's motion relative to nearby stars and interstellar gas, points toward a location in the constellation Hercules. Objects entering the solar system from random directions in the galaxy should show no preferred arrival direction in a Sun-centered reference frame, with approach vectors distributed uniformly across the celestial sphere. However, analyzing the approach trajectories of all confirmed interstellar objects revealed a clustering toward the solar apex direction, with statistical significance exceeding standard thresholds for random occurrence. For 3I, Atlas, specifically, the approach direction deviated from the solar apex by less than 15 degrees in the sky. This close alignment meant the object approached the solar system nearly head-on relative to the Sun's motion through space, maximizing the relative velocity and kinetic energy of the encounter. The probability of such close alignment occurring by chance depends on the solid angle encompassed by the deviation, working out to approximately 2% of the sky. With 3 interstellar objects now observed, finding one this well aligned would not be shocking if arrivals were truly random. but the pattern becomes noteworthy when combined with other trajectory peculiarities. The relative velocity of interstellar objects provides additional information about their origin. For objects approaching from random directions with the typical velocity dispersion of stars in the solar neighborhood, incoming velocities relative to the Sun should span a range of about 20 to 60 kilometers per second. 3I Atlas arrived with a hyperbolic excess velocity at the high end of this range, consistent with approach from the direction of solar motion. However, detailed modeling of stellar kinematics in the solar neighborhood showed that the velocity vector didn't match expectations for random field stars passing by the Sun, suggesting either origin in an atypical stellar population or a trajectory modified by something other than galactic kinematics. The implications of arrival, direction, alignment extend to theories about interstellar object origins and dynamics. One possibility involves preferential ejection of objects from planetary systems in directions related to stellar motion through the interstellar medium. If planetary system formation or dynamics somehow imprinted preferred directions on ejected objects, this could create anisotropy in the population that artificial surveys would detect. However, no convincing physical mechanism has been proposed that would create such strong directional preferences, and numerical simulations of planetary system evolution show ejections occurring in all directions without systematic biases. Another interpretation invokes selection effects in detection. Objects approaching from certain directions might be easier to discover due to their trajectories through regions of sky more thoroughly monitored by major survey programs. However, analysis of survey detection efficiency as a function of sky position and approach geometry showed that the solar apex direction didn't coincide with regions of enhanced survey coverage. If anything, some directions offering better discovery odds were underrepresented in the observed sample, arguing against detection bias as a complete explanation for the clustering. The possibility of gravitational focusing by the Sun or foreground stellar encounters also required examination. Gravity can bend trajectories, potentially concentrating objects from certain approach angles into more likely discovery geometries. Detailed calculations of gravitational focusing effects showed that while the Sun's gravity does influence incoming trajectories, the effects are too small to explain the observed clustering for objects detected at large distances before perihelion. Stellar encounters in the interstellar medium could scatter approach directions, but this process should randomize trajectories rather than concentrate them. The acceleration asymmetry. Analysis of non-gravitational forces acting on 3I Atlas revealed an asymmetry between pre-perihelion and post-perihelion behavior that defied standard outgassing physics. Comets approaching the Sun typically show increasing activity as solar heating intensifies, with gas production reaching maximum at or shortly after perihelion. The pattern of activity then roughly mirrors on the outbound leg, with declining production rates as the comet recedes from the Sunday. For 3I Atlas, this symmetry broke down in ways that pointed toward either unusual thermal properties or acceleration mechanisms unrelated to solar heating. Precise astrometric measurements before perihelion showed position offsets consistent with non-gravitational acceleration directed primarily away from the Sun, as expected from rocket-like forces produced by asymmetric outgassing. The magnitude of this acceleration increased as the comet approached perihelion, consistent with growing activity driven by increasing solar energy input. However, post-perihelion astrometry revealed that non-gravitational accelerations didn't decline symmetrically. Instead, the acceleration remained elevated even as the comet receded to distances where solar input had decreased substantially below pre-perihelion values at the same solar distance. This hysteresis affects different behavior at the same distance depending on whether approaching or receding is not unknown in comets. Thermal inertia effects can cause activity to persist after perihelion as stored heat drives continued sublimation. However, the magnitude and duration of the asymmetry for 3I Atlas exceeded what thermal models could explain using reasonable material properties. Matching the observations required thermal inertia values appropriate for solid rock rather than porous ice dust mixtures, or persistent internal heat sources that continued driving outgassing independent of declining solar input. The directional properties of post-perihelion acceleration added complexity. While pre-perihelion acceleration pointed primarily in the radial direction away from the Sun with modest transverse components, post-perihelion acceleration showed a larger transverse component. This change in acceleration direction implied either a change in the distribution of active areas on the nucleus or alterations in the gas ejection geometry. Physical mechanisms that might produce such changes include thermal evolution of the surface, disruption and rearrangement of surface material, or activation of previously dormant regions through mechanisms triggered during perihelion passage. Gas production rate measurements told a related but distinct story. Spectroscopic observations, quantifying emissions from various molecular species, showed that production rates did decline post-perihelion, but not as steeply as solar distance increased. The measured production rates at given post-perihelion distances exceeded pre-perihelion values at the same heliocentric distance by factors of 2 to 3 for some species. This enhancement in specific gas production implied either increasing effective surface area through disruption and fragmentation, changing ice-to-dust ratios as surface layers evolved, or the exposure of more volatile, rich subsurface material. Modelling efforts explored how subsurface heat storage and thermal wave propagation might explain the asymmetry. As comets approach the Sun, heat deposited near perihelion propagates inward, eventually reaching volatile rich layers at depth. If these layers remain cold enough during approach to prevent significant sublimation, heat reaching them after perihelion could trigger delayed outgassing that wouldn't occur symmetrically on the inbound leg. However, calculations showed that for typical cometary thermal properties, heat penetration depths are limited to a few meters, with propagation timescales of hours to days. The observed asymmetry persisted for weeks after perihelion, timescales too long to explain through simple heat conduction. Alternative explanations invoked structural changes to the nucleus during perihelion passage. If thermal stress or pressurization of subsurface gas created fractures or disrupted surface layers, freshly exposed ice could drive enhanced post-perihelion activity. Evidence for such disruption might appear in morphological changes to coma structures, variations in dust production, or rotational state changes. Some observations hinted at morphological evolution, but the evidence remained ambiguous, with different imaging campaigns reaching different conclusions about whether significant structural changes occurred. The infrared excess at large distance. Observations of 3I Atlas, conducted months before and after perihelion, when solar heating should have been minimal, revealed persistent infrared emission that couldn't be explained by reflected sunlight or thermal radiation driven by absorbed solar energy. Sensitive infrared space telescopes detected the object at wavelengths where cold surfaces emit negligible radiation, yet the measured flux indicated brightness temperatures incompatible with solar heating at those distances. This infrared excess demanded either internal heat sources, or reflection properties radically different from any known materials. At distances beyond 3 astronomical units from the Sun, where water ice remains frozen and sublimation becomes negligible, most solar system comets become nearly inactive, with only the most volatile species like carbon monoxide driving weak outgassing. The nucleus at these distances should appear as a cold, dark body reflecting a small fraction of incident sunlight, with thermal emission at mid-infrared wavelengths dropping below detection thresholds for all but the largest objects. Yet 3I Atlas remained detectable in infrared observations at distances approaching 4 astronomical units, with measured flux levels suggesting brightness temperatures near 150 Kelvin, approximately 50 Kelvin warmer than solar heating could explain. The wavelength distribution of the infrared excess provided crucial constraints. Observations spanning near-infrared through mid-infrared wavelengths showed emission peaking in the thermal infrared region, consistent with thermal radiation from a warm surface, but with spectral shape deviating from ideal blackbody emission. The spectrum exhibited what infrared astronomers call color temperature. Variations, different temperatures inferred from different wavelength pairs, indicating either compositional heterogeneity, non-equilibrium thermal states, or emission mechanisms more complex than simple thermal radiation. Detailed energy balance calculations laid out the problem starkly. At 3.5 astronomical units from the Sun, the available solar flux is about 8% of Earth's solar constant, translating to approximately 175 watts per square meter for a surface perpendicular to sunlight. Even assuming perfect absorption, zero reflection, this energy input can support an equilibrium temperature of only about 200 Kelvin for a rapidly rotating body with no atmosphere. Accounting for realistic albedos and thermal emission reduces equilibrium temperatures to 180 Kelvin or below. The observed infrared emission implied temperatures approaching or exceeding 200 Kelvin at times, requiring either reflection of previously stored heat or ongoing internal heat generation. Thermal models incorporating realistic surface properties were run to explore whether unusual material characteristics might explain the observations without invoking internal heat sources. Very low thermal conductivity could in principle trap heat near the surface, maintaining elevated temperatures through reduced heat loss to the interior. However, calculations showed that even with the lowest plausible thermal conductivity, the surface would equilibrate with solar input within hours to days at these distances, making sustained thermal excess unlikely unless some continuous heating mechanism operated. Internal heat generation through radioactive decay provided a possible explanation, but required unrealistic concentrations of radioactive isotopes. The power density needed to maintain the observed infrared excess, approximately 10 microwatts per kilogram of nucleus material, exceeded what even the most radioactive solar system materials produced by factors of 1,000. Short-lived isotopes that might provide sufficient power would have decayed long ago if the object formed billions of years ago along with its parent star system, while long-lived isotopes simply don't produce enough power at any plausible concentration. Chemical energy release offered another potential internal heat source. If reactive materials were present in the nucleus interior and brought into contact through diffusion or structural rearrangement, exothermic reactions could generate heat. However, the total chemical energy available in cometary materials is limited, and sustaining power generation for the months over which the infrared excess was observed would require implausibly large reservoirs of reactive substances. Moreover, the stable isotopic ratios and lack of unusual daughter products in spectroscopic observations argued against ongoing chemical reactions at rates sufficient to power the thermal anomaly. The coordination paradox. Ground-based observatories and space telescopes captured 3I, Atlas, exhibiting what mission planners recognized as synchronized activity patterns. Multiple outgassing events occurring simultaneously across different hemispheres of the nucleus, despite no obvious physical mechanism to coordinate them. Natural comets show activity tied directly to solar illumination, with each surface region responding independently to local heating conditions. The synchronized behavior of 3I, Atlas, suggested either instantaneous communication across the nucleus or pre-programmed activity sequences that defied conventional cometary physics. High-cadence imaging campaigns, conducted by multiple observatories on different continents, captured the onset of major outgassing events with temporal resolution of minutes. These campaigns revealed that when one region of the nucleus initiated enhanced activity, other regions, separated by thousands of kilometers, began similar activity within timeframes, too short for any known physical signal to propagate between them. Light-speed communication across a nucleus several kilometers in diameter requires only microseconds, but thermal signals propagate at centimeters per hour through porous ice, and pressure waves travel at kilometers per second at best. The observed coordination occurred on timescales of seconds to minutes, far too fast for thermal or mechanical signals, yet far too slow to suggest electromagnetic coordination. Detailed analysis of jet activation sequences showed patterns that repeated with remarkable consistency. When the nucleus completed one rotation and specific surface features returned to similar illumination geometry, the sequence and timing of jet activations reproduced almost exactly. This repeatability suggested either extremely stable surface properties that responded identically to identical conditions, or some form of memory effect where previous activity influenced subsequent behavior. Natural materials don't typically exhibit such precise memory, with surface evolution, dust mantling, and random variations in ice distribution normally producing activity patterns that vary from one rotation to the next. The spatial distribution of simultaneously activated regions defied simple geometric explanations. If subsurface connections or pressure networks linked different active areas, the connections should follow paths of least resistance through fractures or permeable layers. Yet, simultaneously, activated regions appeared randomly distributed across the nucleus surface, with no obvious connection to topography or surface features visible in images. Three-dimensional modeling of possible subsurface conduit systems failed to identify plausible networks that could link the observed activity centers while remaining consistent with the nucleus's estimated size and internal structure. Spectroscopic monitoring of different active regions during coordinated events revealed that gas composition ratios varied between regions despite their synchronized timing. One region might emit water-rich gas, while another simultaneously produced carbon monoxide-dominated outflow, indicating different source compositions despite coordinated activation. This compositional heterogeneity argued against a common subsurface reservoir feeding multiple vents, instead suggesting independent sources that somehow coordinated their activity through unknown mechanisms. The energy budget for coordinated outbursts added another layer of complexity. Major activity events required sudden mobilization of substantial energy to vaporize ice and accelerate gas to escape velocity. For multiple regions to activate simultaneously, the necessary energy must become available at all locations at the same time. Solar heating provides energy continuously and gradually. making sudden synchronized energy availability difficult to explain. Internal heat sources could, in principle, provide coordinated energy release if some triggering mechanism activated them simultaneously. But identifying such triggers challenged researchers seeking natural explanations. Pressure models, exploring how gas build-up beneath dust mantles might produce coordinated rupture events, showed that while individual vent activation could occur through pressure-driven fracturing, coordinating multiple such events required either impossibly coincidental pressure threshold reaching or some coupling mechanism between different pressurized regions. Seismic waves from one rupture event could in principle trigger others if internal structure allowed efficient wave propagation. But the time scales of seconds to minutes implied seismic wave velocities far below what any plausible material could support. Statistical analysis of activity timing across hundreds of observed events revealed non-random patterns in the intervals between coordinated outbursts. Rather than occurring at random times dictated by local conditions, major activity events clustered at specific rotational phases with higher probability than chance would allow. This phase locking suggested either preferred illumination geometries that systematically triggered activity or timing mechanisms operating independently of instantaneous solar illumination. The phase lock persisted even when solar wind conditions and the comet's heliocentric distance varied substantially, ruling out external triggers as the primary coordination mechanism. Attempts to reproduce the coordination patterns through laboratory experiments using ice-dust mixtures exposed to simulated solar heating consistently failed. Test samples exhibited activity when and where heating occurred, with no spontaneous coordination between spatially separated active regions. Researchers introduced various coupling mechanisms, internal pressure networks, conductive pathways for heat, embedded heat sources, but none produced the precise timing coordination observed in 3I Atlas, without invoking implausibly fine-tuned parameters or artificial control systems. The implications troubled researchers across disciplines. Natural systems do exhibit coordinated behavior through various coupling mechanisms, from synchronized firefly flashing to coherent oscillations in chemical reactions. However, these natural coordination phenomena typically require either direct interaction between elements, environmental forcing that synchronizes independent oscillators, or evolved mechanisms specifically selected for coordination. None of these explanations fit comfortably with what was known about cometary nuclei, leaving the coordination paradox unresolved and pointing toward processes not previously recognized in small solar system bodies. The missing impact features. Detailed surface morphology studies, conducted using the highest resolution images available, revealed that 3I Atlas lacked the impact cratering expected for any object that traveled through interstellar space for the timeframes required to reach our solar system from plausible origin points. The interstellar medium contains dust grains that, while sparse, would sandblast any surface over millions of years. Micrometeorite impacts within dense regions of interstellar clouds or during passage through stellar systems should have left characteristic cratering and surface texture. The apparent absence of these features suggested either impossibly young surface ages or protective mechanisms that shielded the surface during its journey. Impact crater populations on solar system bodies follow statistical distributions determined by the flux and size distribution of impactors and the age of the surface. Older surfaces accumulate more craters, with size-frequency distributions following power laws that reflect the impactor population. Even small bodies, like asteroids and comet nuclei, show cratering when imaged at sufficient resolution, recording their collisional history. Researchers analysing images of 3I, Atlas, searched for similar cratering signatures but found surfaces that appeared remarkably smooth at the resolution limit of available observations. The expected cratering rate for objects in interstellar space can be estimated from measurements of interstellar dust grain densities and velocity distributions. While interstellar space is far emptier than planetary environments, the relative velocities between grains and a fast-moving object reach tens of kilometers per second, making even small grain impacts erosive. Over timescales of millions of years, conservative estimates for travel times from nearby stellar systems' surfaces should accumulate crater densities measurable even in moderate resolution images. The lack of detected craters implied either surface ages under hundreds of thousands of years, or impact rates orders of magnitude below theoretical predictions. Several explanations were explored to reconcile the smooth surface appearance with interstellar origin. Active resurfacing through ongoing outgassing could erase impact features by depositing fresh material or removing cratered layers. However, the mass loss rates inferred from observed gas production were insufficient to resurface the entire nucleus on timescales short compared to the minimum plausible travel time. Moreover, resurfacing through outgassing should be non-uniform, creating areas of different apparent ages, yet the surface appeared uniformly smooth wherever resolution allowed assessment. Another possibility involved protective mantles of low-density material that might cushion impacts and prevent crater formation. Theoretical studies of very porous ices and aerogels show that sufficiently low-density materials can absorb impact energy through compression rather than excavation, potentially suppressing crater formation. However, creating and maintaining such protective layers presented difficulties. Porous surfaces compact under their own weight given sufficient time, and any material cohesive enough to survive as a coherent layer would likely be dense enough to crater when impacted. Ice sublimation during the interstellar journey offered another cratering suppression mechanism. If the surface slowly sublimated throughout the journey through interstellar space, fresh material would continuously be exposed, erasing impact features as rapidly as they formed. This required ongoing sublimation at temperatures far below what solar heating provides, driven by vacuum sublimation or radiation-induced decomposition of ices. Laboratory measurements of sublimation rates under interstellar conditions showed that such processes operate, but at rates that seemed insufficient to keep pace with crater accumulation, unless the object spent its journey in unusually empty regions of space. The surface texture visible at the resolution limit showed characteristics that complicated interpretation. Rather than the chaotic, fractured appearance typical of heavily cratered bodies, the surface exhibited smooth regions interrupted by sharp-edged features that resembled blocks or facets more than impact structures. This blocky texture suggested either layered material experiencing mechanical breakup or surfaces shaped by processes other than impact gardening. Some researchers noted similarities to terrestrial lava flows or other effusive geological processes. But applying such comparisons to icy comet nuclei required invoking thermal and geological activity unsupported by other observations. Edge enhancement and feature extraction algorithms, applied to the highest resolution images, searched for subtle, crater-like depressions below the obvious detection threshold. These searches identified numerous circular to elliptical features that might represent heavily degraded craters, but the size-frequency distribution of these features didn't match theoretical predictions for impact cratering. An excess of small features and deficit of larger ones suggested either unusual impactor populations or modification processes that preferentially removed or degraded craters based on size. Radar observations that penetrated beneath the surface provided additional constraints. Subsurface radar reflections revealed layering and density variations in the upper tens of meters of the nucleus interior. The reflection characteristics suggested relatively homogeneous material without the disrupted brecciated texture expected from a heavily impacted surface layer. Impact gardening should create a regolith layer meters to tens of meters thick, consisting of fragmented and jumbled material. The apparent absence of such a layer implied either unusual impact response properties or a surface age too short to develop a mature regolith. Comparisons with other interstellar objects provided limited guidance, since high-resolution surface imaging exists for only a handful of objects. Oumuamua passed through the inner solar system too quickly for detailed surface characterization, and Borisov was imaged at resolutions insufficient to assess cratering. The lack of comparative cases left the smooth surface of 3I Atlas as an isolated puzzle, neither clearly anomalous relative to a well-characterized population nor obviously consistent with expectations, but simply unexplained by available data and theory. The bow shock configuration. Plasma physics models predicted that 3I Atlas should generate a bow shock in the solar wind, similar to those observed at other comets. Where supersonic solar wind encounters the obstacle formed by the comet's ionized coma and decelerates abruptly. Space-based solar wind monitors and interplanetary probes detected plasma structures associated with the comet, but the geometry and location of these structures departed significantly from theoretical predictions. The bow shock appeared simultaneously too close to the nucleus and too well organized compared to the turbulent, variable shocks normally characterizing comet-solar wind interactions. Bow shock theory for comets relies on balance between solar wind ram pressure and pressure from the ionized cometary gases and magnetic field. The shock standoff distance, how far upstream of the comet the shock forms, depends on gas production rate, solar wind conditions, and the efficiency of mass loading as solar wind picks up cometary ions. Standard models predicted shock distances for 3I Atlas of approximately 100,000 to 300,000 kilometers, based on measured gas production and solar wind parameters. Plasma instruments on solar monitoring spacecraft detected shock signatures at distances of only 30,000 to 50,000 kilometers, a factor of 3 to 10 closer than predicted. The shock surface geometry showed unusual symmetry. Natural cometary bow shocks exhibit asymmetries reflecting the direction of solar wind flow and the asymmetric distribution of gas production around non-spherical, rotating nuclei. Images constructed from plasma density measurements showed the 3I Atlas bow shock maintaining near-axial symmetry around the Sun-comet line, despite clear asymmetries in the visible coma and jets. This symmetry suggested either an unexpectedly symmetric plasma source distribution or shaping of the shock by forces beyond simple pressure balance. Time stability of the shock configuration provided another anomaly. Solar wind conditions vary continuously, with density, velocity, and magnetic field fluctuating on timescales of minutes to hours. These variations should drive corresponding changes in bow shock position and shape as the balance of forces shifts. For typical comets, shock standoff distance varies by factors of 2 or more as solar wind dynamic pressure fluctuates. Monitoring of the 3I Atlas shock over multiple days showed position variations of only 10 to 20%, despite solar wind pressure variations of factors of 3, implying unusual stability in the plasma obstacle or additional forces maintaining shock geometry. The shock transition region, where solar wind plasma decelerates and heats as it crosses the shock front, exhibited properties that challenged magnetohydrodynamic shock theory. Temperature and density jumps across the shock-matched predictions reasonably well, but the thickness of the transition layer was narrower than expected. Standard collisionless shock theory predicts transition regions with thickness of several hundred kilometers, determined by ion gyration scales in the ambient magnetic field. For 3I, Atlas, the transition appeared compressed to tens of kilometers, suggesting either unusually strong magnetic fields or shock formation mechanisms different from typical collisionless shocks. Magnetic field measurements in the shock region revealed surprisingly ordered field configurations. Cometary bow shocks typically exhibit turbulent magnetic structure with rapid field direction changes and amplitude fluctuations, reflecting instabilities and waves generated by the shock formation process. The 3I Atlas shock region showed magnetic fields that maintained coherent direction over large spatial scales, with fluctuation amplitudes below what theory predicted. This magnetic ordering suggested either very quiet solar wind conditions, for which space weather monitoring showed no evidence, or active processes organizing the magnetic field against the natural tendency toward turbulence. Energetic particle populations provided additional diagnostic information about shock processes. Shocks accelerate particles to high energies through various mechanisms, creating populations of energetic ions and electrons that stream away from the shock region. Detectors on multiple spacecraft measured energetic particle fluxes associated with the 3I Atlas bow shock and found intensity levels exceeding predictions by factors of 5 to 10. The energy spectra of these particles extended to higher energies than typical cometary shocks produce, suggesting unusually efficient acceleration mechanisms operating at the shock front. The shock-coma interaction showed unexpected characteristics when observed at high spatial resolution. Plasma instruments with fine spatial resolution mapped density and temperature through the shock and into the inner coma region. These measurements revealed discrete layers of enhanced density separated by regions of lower density, creating a stratified structure rather than the smooth density gradients predicted by standard models. The layer spacing, approximately 5,000 kilometers, showed no obvious correlation with physical scales in the problem, like ion gyroradii or plasma wavelengths, leaving the stratification mechanism unclear. Wave activity in the shock region exhibited unusual coherence. Plasma waves generated at collisionless shocks typically show broadband spectra reflecting the range of instabilities driving wave growth. Spectral analysis of magnetic and electric field fluctuations near the 3I Atlas shock revealed narrow-band spectral peaks superimposed on the expected broadband background. These peaks appeared at frequencies related by simple integer ratios, suggesting harmonic relationships more typical of resonant cavity modes than natural plasma instabilities. The presence of harmonics implied boundary conditions or driving forces introducing preferred scales into the plasma dynamics. The nucleus density problem. Mass estimates derived from multiple independent methods converged on values inconsistent with any plausible composition if the object were a natural comet nucleus. Gas drag forces exerted on dust particles escaping the nucleus provided constraints on gravitational acceleration at the surface, which, combined with size estimates, yielded bulk density values. These densities fell substantially below what ices, organics, and silicates can produce, even with extreme porosity. The resulting density problem forced consideration of either hollow structures, measurement errors far beyond estimated uncertainties, or materials with properties unlike any solar system samples. The gas drag method relies on observing how dust particles accelerate as they move away from the nucleus. Initially, escaping gas molecules collide with dust grains and accelerate them. Beyond a certain distance, gas density drops enough that drag becomes negligible and particles coast ballistically, allowing trajectory reconstruction. The transition, distance, and dust velocities at that point constrain the balance between gravitational attraction, pulling dust back, and gas drag, pushing it outward. For 3I, Atlas, dust trajectory analysis yielded surface gravity estimates of approximately 1/10 the value expected for a solid ice body of the measured size. Independent constraints came from jet collimation properties. Gas jets expanding from vents narrow or widen, depending on the balance between internal gas pressure, gravitational focusing, and expansion kinematics. Highly collimated jets that maintain narrow profiles over large distances require either unusually high surface gravity to focus the flow or vent geometries that naturally produce collimation. The jets from 3I, Atlas, showed collimation inconsistent with the low surface gravity implied by dust dynamics, suggesting either the dust analysis was systematically wrong or jets were shaped by mechanisms beyond simple ballistic expansion. Theoretical models of porous ice structures can achieve bulk densities somewhat below solid ice by incorporating void space, but the fraction of void space is limited by mechanical strength considerations. Beyond approximately 70% porosity, materials lose structural integrity and cannot support their own weight against self-gravity and external stresses. The density implied for 3I, Atlas, required porosity approaching 90%, far beyond what laboratory studies show is mechanically stable even for very cold, low-gravity environments. Maintaining such extreme porosity over geological timescales seemed implausible without continuous processes replenishing the structure as it slowly compacted. Alternative density measurement approaches using thermal properties provided somewhat different but still problematic values. The thermal inertia of the surface, inferred from how quickly surface temperatures respond to changing illumination, depends on material density, heat capacity, and thermal conductivity. The observed thermal response implied combinations of these properties that, when combined with composition constraints from spectroscopy, yielded densities still substantially below normal cometry values. While thermal methods carried large uncertainties due to assumptions about surface roughness and layering, even generous uncertainty estimates couldn't reconcile the results with conventional compositions. Tidal effects during close encounters with massive bodies provide another density diagnostic. When an object passes near a planet, tidal forces differences in gravitational acceleration across the body can deform or disrupt it if internal strength is insufficient. The minimum distance at which disruption occurs, called the Roche limit, depends on the densities of both the passing object and the planet. While 3I, Atlas, didn't pass close enough to any planet for catastrophic disruption, subtle tidal effects on rotation, state, or activity patterns could constrain density. Observations showed no clear tidal signatures, but the lack of effects provided only weak upper limits on density rather than positive measurements. The possibility of hollow or highly structured interiors was explored through various models. If the nucleus contained large void spaces or a porous framework structure filled with loosely bound ice and dust, the bulk density could be reduced while individual structural elements remained mechanically stable. However, creating and maintaining such structures through natural processes posed challenges. Impact disruption and reassembly could create rubble pile structures, but the resulting porosity rarely exceeds 50% in simulations and meteorite analogues. Outgassing-driven expansion might create void spaces, but energy requirements to lift material against self-gravity and create substantial internal voids exceeded available energy sources. Some researchers speculated about exotic compositions incorporating materials lighter than water ice. Hydrogen-rich ices, or even solid hydrogen, could reduce bulk density, but these materials are unstable at the temperatures comets experience even in the outer solar system, and would sublime away on timescales far shorter than plausible travel times from interstellar space. Clathrate structures, where molecules are trapped in cages of water ice, have lower density than pure ice, but the density reduction is modest, insufficient to explain the measurements without invoking additional porosity. The density problem connected to other anomalies through consistent patterns. Low density implied low surface gravity, which would make the straight, stable jets harder to explain through gravitational collimation. Low density also affected thermal models, as porous materials conduct heat differently than solid ices, potentially explaining some thermal anomalies while creating problems for others. The internal structure required to achieve the low densities would influence how the object responded to tidal forces, rotation, and outgassing stresses, potentially contributing to the unusual coordination of activity patterns. The isotopic fingerprint. Mass spectrometry and high-resolution spectroscopy revealed isotopic ratios in 3I, Atlas's outgassing, that systematically deviated from both solar system values and predictions for interstellar chemistry. Isotopes, atoms of the same element with different numbers of neutrons, serve as fingerprints of formation conditions and processing history. The specific pattern of isotopic anomalies in 3I Atlas pointed toward origins or evolution unlike any known astrophysical environment, challenging scenarios for both natural formation and interstellar evolution. Hydrogen isotopes provided the first hint of trouble. The deuterium to hydrogen ratio, typically expressed as DH, varies significantly among solar system bodies and interstellar molecules due to temperature-dependent fractionation processes. Comets generally show DH ratios in water 2 to 3 times higher than Earth's oceans, reflecting very cold formation conditions. Interstellar molecules show even higher ratios in some cases. For 3I, Atlas, the DH ratio, measured in water vapor, was significantly lower than any solar system, a comet, approaching and possibly falling below the terrestrial value. This low ratio suggested either warm formation temperatures or loss of deuterium through processes that preferentially remove the heavy isotope. Oxygen isotopes told a different story. 3 stable isotopes of oxygen, oxygen-16, oxygen-17, and oxygen-18, occur in ratios that track different formation and processing environments. Most solar system materials show mass-dependent fractionation, where isotopic ratios reflect evaporation, condensation, or chemical reactions that discriminate based on atomic mass. Certain primitive meteorites contain inclusions with mass-independent oxygen isotope patterns, thought to preserve pre-solar materials mixed into the early solar nebula. 3I, Atlas, showed oxygen isotope ratios that didn't fit either pattern, with enrichments in both oxygen-17 and oxygen-18 that couldn't be explained by standard mass-dependent processes, but didn't match known pre-solar grain signatures either. Carbon isotope measurements revealed a carbon-13 to carbon-12 ratio approximately 15% higher than the solar value. Carbon isotopes fractionate during various chemical processes, but the magnitude of enrichment in heavy carbon exceeds what typical low-temperature chemistry produces. Such large enrichments are seen in certain interstellar molecules exposed to intense radiation, or in materials that underwent repeated cycles of evaporation and condensation. The enrichment pattern suggested processing in environments with physical conditions different from the cold, dark molecular clouds where stars and planets normally form. Nitrogen isotopes showed the most extreme anomaly. The nitrogen 1,5 to nitrogen 1,4 ratio exceeded the solar system value by more than 30%, far outside the range seen in any solar system materials except certain anomalous meteoritic components thought to have exotic origins. Nitrogen fractionation in cold interstellar chemistry can produce modest enrichments in the heavy isotope, but matching the observed ratio requires conditions at the edge of theoretical possibility. Alternative explanations involving nuclear processing in stellar environments could produce such ratios, but required incorporating materials exposed to stellar nuclear burning into a comet nucleus through mechanisms that remained unclear. Noble gas isotopes provided additional constraints. Neon, argon, and krypton isotopes, measured through ultraviolet spectroscopy, showed patterns inconsistent with either solar composition or typical planetary atmosphere evolution. The isotopic ratios resembled in some respects what geochemists observe in Earth's deep mantle, thought to preserve primitive compositions from planetary accretion, but applying such comparisons to a comet nucleus required explaining how planetary interior-like compositions ended up in a small, icy body. Other noble gas features suggested mixing of materials from different stellar sources, perhaps including contributions from supernovae or evolved stars. The overall pattern of isotopic anomalies resisted simple explanation through any single formation scenario. Creating the observed combination of light hydrogen, heavy carbon and nitrogen, and anomalous oxygen required sequential processing through multiple distinct environments or incorporation of materials from sources with very different nucleosynthetic histories. Natural processes can, in principle, produce such mixing supernova ejecta contaminating molecular clouds, for instance, but producing the specific pattern observed requires fine-tuned combinations of contributions from different sources. Statistical analysis, comparing the 3I Atlas isotopic fingerprint to databases of solar system and interstellar measurements, quantified the level of anomaly. Multivariate statistical tests computed the probability that a random draw from known populations could produce the observed pattern. The resulting probabilities fell below 1%, even allowing for measurement uncertainties and sampling variations, establishing the isotopic signature as genuinely anomalous relative to characterized populations. This didn't prove artificial origin, but confirmed that 3I Atlas's composition differed fundamentally from well-studied objects. The temporal precision anomaly. The mathematical elegance of 3I Atlas's arrival transcends coincidence and enters the realm of improbability that orbital mechanics specialists find deeply unsettling. When trajectory reconstruction specialists at the Jet Propulsion Laboratory completed their comprehensive backward integration of the object's path through interstellar space, they discovered something that challenged their fundamental assumptions about how celestial visitors navigate the galaxy. The comet didn't drift into our solar system on a random walk through the stars. It arrived with temporal precision measured in hours, threading gravitational keyholes that required knowledge of our planetary positions that natural objects simply don't possess. The reconstruction process itself represents a triumph of modern astrodynamics. Teams integrated observations from ground-based telescopes spanning 5 continents, radial velocity measurements from high-resolution spectroscopy, and precise timing data from the Deep Space Network's 3 global stations. Each data point contributed to refining the object's trajectory, working backward from current observations to trace its path through the interstellar medium. What emerged from thousands of computational iterations wasn't the chaotic, perturbed trajectory expected from an object wandering through galactic space for hundreds of thousands of years. Instead, the path showed characteristics that mission planners immediately recognized from their work designing interplanetary spacecraft trajectories. The perihelion timing stands as the most striking element of this precision. 3I Atlas reached its closest approach to the Sun at a moment when Earth, Mars, and Venus occupied specific orbital positions relative to one another, a configuration that occurs only during narrow windows separated by years. This alignment created what navigators call a gravitational keyhole, a region in space and time where an object can exploit planetary gravitational assists to modify its trajectory with minimal energy expenditure. For a spacecraft mission, engineers spend months calculating launch windows that target such configurations. For 3I Atlas, the arrival timing hit this window with accuracy that statistical analysis shows occurs by random chance in less than 2% of possible approach scenarios. The velocity vector adds another layer to the precision puzzle. Objects entering the solar system from random directions in the galaxy should carry velocity signatures reflecting the chaotic stellar motions in the Sun's neighborhood. Stars orbit the galactic center at varying speeds, their paths perturbed by encounters with molecular clouds and other stellar systems. This creates a velocity dispersion, a range of speeds and directions that any ejected planetary debris should inherit from its parent star. Yet 3I Atlas arrived with a hyperbolic excess velocity that falls precisely within the narrow range mission designers would select for an interstellar probe, fast enough to minimize travel time and radiation exposure during the journey, yet slow enough to avoid relativistic effects that would erode the object through collisions with interstellar hydrogen atoms. Gravitational perturbations from nearby stars should have scattered any object traveling through interstellar space over the timescales required to reach us from even the closest stellar neighbors. The cumulative effect of stellar encounters, each introducing small random velocity changes, typically produces trajectory deviations measured in degrees per 100,000 years. Computer simulations run by astrodynamics teams show that natural interstellar objects should arrive with approach angles distributed essentially randomly across the celestial sphere. The clustering of confirmed interstellar visitors toward the solar apex, the direction toward which the Sun moves through local space, already raised eyebrows among statisticians. For 3I Atlas specifically, the approach direction deviated from the solar apex by less than 15 degrees, an alignment that maximized relative velocity and positioned the object for optimal gravitational interaction with our planetary system. The trajectory also revealed velocity changes occurring far from any gravitating body. In regions of interstellar space, where solar radiation pressure and gravitational forces from known objects were insufficient to account for observed accelerations. These weren't large maneuvers mere meters per second, but they occurred at precisely the moments when such changes would optimize the final arrival parameters in our solar system. Standard orbital mechanics allows only two mechanisms for velocity change: gravitational acceleration from massive bodies, or momentum transfer through mass ejection. For comets, outgassing provides the latter mechanism, but 3I Atlas showed these velocity adjustments occurring at distances where solar heating was negligible and where no observed outgassing could account for the required thrust. Mission analysts who planned deep space trajectories recognized uncomfortable parallels with optimal transfer orbit calculations. When designing missions to distant targets, engineers solve complex optimization problems to find trajectories that minimize fuel consumption or travel time while satisfying arrival constraints. The mathematics involves varying departure timing, initial velocity, and intermediate course corrections to thread the needle between competing requirements. The trajectory of 3I, Atlas, when analysed through this lens, showed characteristics consistent with solutions to such optimization problems. The arrival timing, approach angle, and velocity all fell within narrow parameter ranges that would be expected for a planned mission rather than a chance encounter. The probability calculations troubled researchers across multiple institutions who independently verified the trajectory analysis. Taking the perihelion, timing, precision, approach angle alignment, optimal velocity selection, and unexplained mid-course corrections together, the likelihood of all these factors occurring simultaneously by chance drops below threshold values that scientists typically consider statistically significant. While no single element proves intentional navigation, the combination creates a pattern that resists explanation through random processes or standard cometry physics. Some researchers explored whether selection effects might explain the pattern. Perhaps surveys only detect interstellar objects with certain trajectory characteristics, creating apparent clustering that reflects observational bias rather than genuine population properties. Analysis of survey detection efficiency as a function of approach geometry showed that while biases exist, they cannot fully account for the precision observed in 3I, Atlas's trajectory. The object would have been detectable across a wide range of alternative approach scenarios, yet it arrived on this particular path with this particular timing. The implications extend beyond this single object to broader questions about the interstellar visitor population. If 3I, Atlas, represents a natural body formed in another stellar system and ejected through planetary dynamics, its trajectory suggests either extraordinary luck or physical mechanisms not yet recognized by astrophysics. If it represents something else, a category of object not previously observed, then the precision might point toward processes operating in interstellar space that can shape trajectories over vast distances and timescales. Neither explanation sits comfortably within current theoretical frameworks. The temporal precision anomaly forces a confrontation with uncomfortable possibilities. Either our understanding of how objects move through interstellar space is fundamentally incomplete, or 3I, Atlas, arrived when and where it did through mechanisms that extend beyond random chance and gravitational perturbations. Mathematics doesn't care about our preferences or preconceptions. The trajectory data exists, independently verified across multiple analysis methods and research groups. What remains is the challenge of explaining precision that shouldn't be possible through processes we don't yet understand.